Monte Carlo analysis is used to evaluate output uncertainty and when analytical solutions are difficult or do not exist. Basically, a CDF is developed for uncertain inputs, and each CDF is randomly sampled numerous times by randomly generating a number between 0 and 1, and then sampling the corresponding random variable. This is called inverse transform sampling. The output distribution is built up over multiple iterations or trials and is repeated over and over again. With enough iterations, the output mean will converge, and we end up with a probability distribution of the model outputs. For a Monte Carlo analysis, each sample is entirely random and can fall anywhere within the range of the input distribution. It essentially samples a uniform distribution from 0 to 1, then transforms those values by pulling from the CDF. New samples are generated without taking into account previous samples. Sometimes consecutive samples will be close to each other, other times they will be far apart. For that reason, a large number of samples is necessary to adequately sample the tails of a given distribution using the Monte Carlo sampling method. Because we know the equations for the CDFs of several probability distributions, we can perform simple Monte Carlo analyses in Excel without using a program like @RISK. This is the method that you'll find in many of the geotechnical toolboxes that are out on the RMC website. In this example, we're going to set up a triangular distribution in Excel. We will use the rand function, a function that is built into Excel, to randomly return a number between 0 and 1. We will use these random numbers to sample from our distribution CDF by setting f of x equal to the random number, then solving the CDF equation for x. We will repeat this for however many iterations we want to do. Because the CDF equation for a triangular distribution is different on either side of the mode, we will need an if statement. In the first part of the if statement, we will check to see if the x is between a and b, the lower bound and the most likely value, or if it's between b and c, the most likely value and the maximum value. Once we figure out which side our x will be, we pick the proper equation and solve for x. The equation in the middle of the screen is for when x is between a and b, and the equation at the end is when x is between b and c. So, f of x is equal to a random number between 0 and 1. We know what a, b, and c are, so we can solve for x with each iteration to sample our triangular distribution. In this example, we only did 10 iterations, which is woefully inadequate. We would do many more in practice, but once we have all our points, all our x values, we can then use them to develop a CDF. To develop the CDF, rank and sort the values from low to high. The cumulative probability for a given x value will be its rank divided by the number of iterations, and it will give the CDF shown here. If we were to up the number of iterations to 1,000, the CDF looks much better. We get the nice S-curve, and we do a pretty good job of estimating the median and the mean of the distribution. The tails of the distribution would be better represented if we did even more iterations. Another sampling method is Latin hypercube, which is the default method used by @RISK. This method will recreate the input distribution with fewer samples than it will take for Monte Carlo sampling. Latin hypercube sampling divides the cumulative distribution function into equal intervals based on the number of iterations selected for the simulation. Let's say we wanted to do 4 iterations. This sampling method will split the CDF into 4 even intervals. Then a single sample is randomly selected from each of these intervals. As a result, even for a small number of iterations, the Latin hypercube method makes all or nearly all sample means fall within a small fraction of the standard error. So if we go back to the 10 iteration example we stepped through prior to the exercise and compare the results of Monte Carlo sampling versus Latin hypercube sampling, you can clearly see that Latin hypercube sampling does a much better job of matching the expected distribution with the limited number of iterations. One thing to be conscious of is what can result when samples are independent in a Monte Carlo or Latin hypercube analysis. If we are not careful, sometimes the distribution results can be physically impossible for things like system response probabilities or consequence relationships. So let's say I've used a distribution to define the system response at each stage. If samples are taken independently, the general shape of the system response curve is not maintained and is not monotonically increasing with stage for the iteration shown. The resulting curve increases, then decreases, then increases again, then decreases again. A system response curve cannot do that. One way around this is consistent percentile sampling. A percentile is sampled and the corresponding system response probabilities for that percentile are selected for each stage. This can be accomplished simply in practice by correlating the system response probabilities versus stage. This way, the proper shape of the system response curve will be maintained with each iteration. Here is another example, this time for life loss consequences instead of the system response. You can see the results of independent sampling on the left and how consistent percentile sampling cleans things up on the right. This is what consistent percentile sampling would look like when sampling the stage frequency curve. You can see the general shape is maintained with each iteration.